Hello, everyone.
Calculus can apply to. And now that we've learned about implicit differentiation, we are ready to look at one such application, the concept of related rates. Let's say we are inflating a balloon, and let's pretend that the balloon is a perfect sphere. So we essentially have a sphere that is expanding at a constant rate. Now say we want to describe the rate at which the volume of the sphere is increasing, as well as the rate at which the radius of the sphere is increasing. Both of these values are increasing due to the expansion of the balloon, and their rates of increase are related, hence related rates. But one of these is probably much easier to physically measure than the other. So rather than trying to measure both, let's measure the one that we can and compute the rate of change in the other using calculus. It's probably easier to measure the change in volume. So let's say that we do measure the volume over some period of time, and we find that it is increasing by 100 cubic centimeters per second. How can we use this to find out how fast the radius is increasing at a particular instant, like the moment when the diameter of the balloon is 50 centimeters? Well, let's say that volume is V and radius is R. Then dV over dt, or the change in volume over time, equals 100 cubic centimeters per second, as we measured. But what we want to know is dr over dt, or the change in radius over time, at the moment that the radius is 25 centimeters, since the radius is half the diameter. To see how these values will relate, we need an equation that relates V and R, and that will be the equation for the volume of the sphere. When we learned geometry, we saw that this formula is V equals 4/3 pi r cubed. Now, as we said, what we are looking for is dr over dt, so let's differentiate this with respect to t. For V, that simply becomes dV over dt, but for the right side, we will need to use the chain rule. This is because t is not present in this equation. The radius is the variable, but the radius is itself a function of t, which is why we use the chain rule. So we will have to differentiate this expression with respect to r, and then multiply that by the derivative of r with respect to t, or dr over dt. The derivative with respect to r is easy. We just bring the 3 down here and change the 3 to a 2, giving us 4 pi r squared. And then that must be followed by dr over dt. Well, dr over dt is what we are trying to solve for, because we are interested in how the radius changes over time. So let's solve for that. This means simply dividing both sides by 4 pi r squared. That means that dr over dt equals dv over dt times 1 over 4 pi r squared. We plug in our value for dv over dt, which is 100, and the value for r that we are interested in, which is 25. We evaluate, and we get 1 over 25 pi centimeters per second. Let's try another example. Say we have a ladder resting against a wall. The ladder is 10 feet long, and it is sliding away from the wall at a rate of 1 foot per second. How fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet away from the wall? Just as with any other example we could look at, we will quickly see that we need to be able to construct equations that represent the scenario. Looking at the diagram, we have a ladder with a constant length of 10, and then these values are the variables x and y, as they both change over time. So that makes a right triangle with a known hypotenuse and the 2 legs unknown. We can relate the variables by the Pythagorean theorem. That would be x squared plus y squared equals 10 squared, or 100. Now, as we said, we want to know how these parameters change over time. So let's differentiate both sides of this equation with respect to time. The derivative of x squared with respect to time will be 2x times dx over dt. For y, we get the same thing, 2y times dy over dt. On the right, the derivative of any constant is 0. Now, we want to know about how fast the ladder is sliding down the wall, which is described by dy over dt. So let's solve for dy over dt. We take the term with all the x's to the other side, and then we divide by 2y, and we get negative x over y times dx over dt. So all we have to do is plug in what we know and solve. We are asking about dy over dt when the ladder is 6 feet away from the wall. That means x must be 6. Then, by the Pythagorean theorem, we can solve for y at that instant, and that must be 8. We can also plug in dx over dt because we said that the ladder was sliding away from the wall at 1 foot per second. That means x is increasing by 1 foot every second. So dx over dt is positive 1. We simplify and we get negative 3/4 feet per second. This is a negative value because y is decreasing over time as the ladder slides down the wall. So as we can see, related rates problems can be rather straightforward. The real challenge lies in understanding what the problem is asking and being able to first draw a diagram. Then we must write equations from that diagram that relate the 2 variables in question. Because we are describing rates, these will always be functions of time, and we will be taking derivatives of functions with respect to time. This may require the chain rule, as we may be taking the derivative of a function first with respect to some variable. So we must then multiply by the derivative of that variable with respect to t, since we are ultimately concerned with terms involving dt. Once we have done that, we just plug in the information we know and solve for what we are looking for, which will always be d something over dt. Thanks for watching, guys.